Sound and light are obviously two very different things. Sound needs a medium in which to travel. So these are pressure waves. There's compression, rarefaction. And so energy travels along in a given direction through one part of the medium pressing on the other part. But light doesn't need any kind of a medium. So then it's really quite mysterious, isn't it, that they exhibit the same kind of phenomena, by which I mean interference. So if you have light waves or you have sound waves, they both can interfere with each other. And so you have the famous double slit experiment, which we'll cover. You also have diffraction. So even if you have a single little hole in something, then light or sound both can spread out. And this is what enables sound to bend around corners. Also light to do that, except you don't see it that much. So then the question is why? And the answer was given a couple of 100 years ago, or maybe more, by a man, a Dutch physicist called Huygens. We're going to study Huygens' principle at the end of this lecture. And it'll appear a little mysterious because you'll say, where did this come from? And the answer is, it comes from the wave equation that you studied earlier on in the previous lectures. From the wave equations, you can actually prove Huygens' principle. But we'll come to that once we begin our understanding of interference of waves. At the very beginning, I want to talk about energy and intensity in a sound or a light wave. But before I get to waves, I want to talk about a simple harmonic oscillator, one that you've seen many times before, but I need to quickly review some ideas about this. So let's say that this is a spring which is fixed at one end. There's a mass which can oscillate. This is frictionless over here, so it will, if you set it in oscillation, it will keep oscillating forever. Now, just to be definite, let's call this the mass m, this the spring constant k, and so obviously the oscillation frequency omega squared is k over m. And if you were to solve the equation for this, you get that x as a function of time is x naught, either sine of omega t or cosine of omega t. Now, x0 is what we call the amplitude. You know that very well. It's the maximum value that x can take away from its equilibrium position. Okay, if we look at the potential energy, then that's half the spring constant into the extension squared, half kx squared. And so if you put in x equal to this over here, well, obviously you'll get half k x naught squared sine squared omega t. Now, because k is m omega squared, you can write this as half m omega squared x naught squared sine squared omega t. So the potential energy is 0 when it is at the equilibrium position, and it is maximum when it is maximally stretched. That's the potential energy. The kinetic energy, well, that's just half the mass into the speed squared. So that's x dot squared. X dot is dx by dt. And if I differentiate this, then I get half m omega squared, and of course that omega comes from differentiating the sine, and there's a cosine over here, cosine squared omega t. Okay, if I now add both the potential and the kinetic energies, here's what I get. I get the total energy is the sum of the two, so it's half m omega squared x naught squared. There's sine squared omega t, and you add to that cosine squared omega t, and that's independent of time. That's just half m omega squared x naught squared. Now you see, the reason I'm repeating all this is that there's some important features. First of all, the energy is proportional to the amplitude squared. And secondly, to the square of the frequency. And of course, the heavier it is, that is, the greater the mass, the greater the total energy. Now, this assumed that there was no damping, that this would keep going on and on forever. And this might be a good approximation in some situations, but it's not a perfect approximation. So there is a way in which you can include friction. I won't go into that because it'll take too much time, but it's you can see actually what that will lead to. So if you have damping means that there's some frictional force which is causing this to slow down. Well, that has the form x equals x naught sine omega t. But now this is multiplied by something that decreases with time. So this is e to the minus gamma t. And actually this comes out of a proper calculation, but let's take it as it is. Now the exponential function, you should know that if I have x and e to the minus x over here, it starts from 1 and then it decreases and goes to 0 eventually. So obviously as time goes on, this factor over here becomes closer and closer to 0, starting from 1. All right, now I'll leave this as an exercise. If you put x in here and x in here, then you will get the potential energy and the kinetic energy as a function of time. And what you will find is this. So do this as an exercise. It's very easily done. So in the absence of damping, it was just this. In the presence of damping, well, what do you expect? It will be e to the minus 2 gamma t, because basically you have squared this. Now, this is something that you have to go out and verify, and this will hold if gamma, that is to say the damping, is very small. So if it is very small, then the oscillator will keep on oscillating, but its amplitude will decrease with time and the total energy will also be lost. Well, lost in the sense that it will be gained by something, by the surface against which it is rubbing itself. Okay, now let's go on to waves. And here I'm talking of sound waves. Here, the energy in a sound wave, I'll just write down the answer because it'll take us too long to derive. It's very, very similar to what you have over here. The difference is that instead of the mass of this thing over here, I have the density of air, or whichever medium that sound is traveling in. There's the square of the frequency, and then there is the amplitude A squared. So if I have a sound wave which is like this, epsilon of x t, that's the displacement, is a sine of kx minus omega t. Well, that's the A, that's the amplitude here. And so the important thing is that the energy in a wave is proportional to the square of the amplitude. And it's so important that I'm going to write this in the following way. So energy is proportional to amplitude squared. Now, amplitudes you can always add together, and we will see that that will lead us to some very interesting physics. However, before we move on, I want to talk about sound waves. Is there friction in a sound wave? Is there dissipation? Well, that's the question, that if I have sound that is traveling in one direction, and so these are plane waves, will their intensity, will their energy decrease as they move along? And the answer is, it's not perfect. So the energy does decrease, but very slightly. And so sound can propagate a long distance. Now you'll ask, why does the energy decrease slightly? Why does it decrease at all? And the answer is that as a sound wave goes along, then there's compression, rarefaction, and some molecules then get hit by others, and so some heating of the air happens when sound travels through it. But it's very, very little, and so we will assume, for what's going to come next, assume that this can be neglected. So I'm going to work under the assumption that a plane wave, as it moves in one direction, will not lose any energy. We've seen that plane waves don't lose any energy, but what about waves in 2 dimensions or 3 dimensions? By 2 dimensions, I mean the following. Suppose there's a still pond and you drop a stone. Well, the waves will start moving out, and energy will be carried outwards like this. Okay? Now, I'm going to assume that there is no frictional loss, no dissipation, but you see that the energy per unit length is going to decrease as we go outwards. So let's put this down mathematically. If I take a circle of radius r, then its circumference is 2 pi r, and so the energy of the wave that is located at r, so you can think of this as a pulse, then that E will be equal to 2 pi r times the intensity. So this is the energy per unit length. So the pulse is carrying energy outwards like this in all directions, here, etc. Now this energy is constant, assuming that there is no dissipation, assuming that there is no friction. So this is a constant, which means that this I, which is the energy per unit length, is going down as 1 over r. But this is energy. This means that the amplitude, remember, is the square root of the energy. So, as we saw in the harmonic oscillator, the energy is proportional to the amplitude squared. Correspondingly, the amplitude is proportional to the energy square root. And so the amplitude goes down as 1 over the square root of r. And therefore, in 2 dimensions, we've discovered that the amplitude of the wave that spreads out will decrease as the square root of the distance from the center. So that was for 2 dimensions. In 3 dimensions, we have again the same situation. So let's say that there's a source of disturbance and a pulse moves out, and of course it'll move out in all directions equally. And now this over here, I can't draw it as a sphere, I've drawn it as a circle, but you understand that this is actually 3-dimensional. And so the total energy of the pulse, that will be the area of this surface, which will be 4 pi r squared. That's the area of a sphere with radius r times I. And now this, the total energy is conserved because we are assuming that there is no dissipation, in which case this is a constant. And so in 3 dimensions, the intensity will decrease as the square of the distance from the center. So this is what is called the inverse square law. Now, if the intensity decreases as the square, that means that the amplitude will decrease as 1 over r. And so these are 2 important results that we found over here. That for 2 dimensions, the amplitude decreases as 1 over square root r, and for 3 dimensions, it decreases as 1 over r. So far, I've talked only about one wave. But if there are 2 waves, then they can interfere with each other. Let's therefore discuss the interference of 2 waves. Well, we can discuss later the interference of 3 waves, 4 waves, and many, many waves, but that will come later. Let's take the simplest example first. So, suppose that I'm standing here, and there's a loudspeaker or some source of sound here which is sending out waves towards me. And those waves are of amplitude, the ones that I receive over here, so that's me here. Let me draw myself. The wave that I receive is epsilon 1, which is epsilon naught, either sine or cosine, doesn't make a difference. Let's take this cosine of kx minus omega t, and always omega and k are related through the speed of sound, c. Now, this was from source number 1. Suppose I have a second source, and that second source is just behind this, but I won't draw it exactly over there. So the second source is a distance delta x behind it. And let's call this S2. Now this second source is also sending out waves of the same frequency to me. And the waves that I receive from the second source are exactly the same in frequency, but they started out earlier. So x plus this small amount over here, delta x, minus omega t. And of course, I insist over here that these are identical sources. So this could be a loudspeaker and this another loudspeaker connected to the same amplifier, to the same source. Now, as we just learned, the intensity is proportional to the amplitude squared. And that's E1 plus E2 squared. Okay, so let's put that in. That's epsilon naught squared. And here I have cosine of kx minus omega t plus cosine of kx plus delta x minus omega t. And I must square them after adding. Okay, so here I have the sum of two cosines. And now you remember that the cosine of A plus the cosine of B is 2 cosine of A plus B, that is to say the sum of the angles divided by 2. So this is cosine of kx minus omega t plus delta k delta x over 2. And then the difference between this angle and this angle, so that's cosine of k delta x over 2. Now let's square this. So this is epsilon naught squared. There's 4 over here coming from 2 squared. And I have cosine squared of kx minus omega t plus k delta x over 2, cosine squared of k delta x divided by 2. Now, this is very, very interesting because this cosine of k delta x by 2 can sometimes be 0 and sometimes as big as 1. Of course, it can never be negative. This is the square of the cosine. So let's notice 2 extreme cases. One is when there's zero intensity. Zero intensity of sound that's reaching me here when both the speakers are on. So zero intensity happens when this thing is 0. So when cosine of k delta x by 2 is 0. Well, that means, obviously, that k delta x by 2, the cosine is 0 when this is pi by 2, or when it is 3 pi by 2, or when it is 5 pi by 2, etc. Okay, now recall that k is 2 pi divided by lambda, and so this says that I must have 2 pi delta x by lambda is either pi, 3 pi, 5 pi, etc. And that says that for a minimum delta x will be either lambda by 2, that is half the wavelength, or 3 lambda by 2, etc. And this is what is called destructive interference. On the other hand, we could have the two waves adding up together with each other. So for maximum intensity, it's the other case. So that happens when cosine of k delta x by 2 is equal to 1, which means that this over here is either 0, so k delta x by 2 is equal to 0, or it is pi or 2 pi. Well, I should say that this cosine squared of k delta x by 2 is equal to 1, because cosine can be positive or negative. that when this over here is pi, then of course this will be -1, but -1 squared is 1. And so 0, pi, 2 pi, 3 pi, etc. That makes delta x is either 0 or lambda or 2 lambda or 3 lambda. So compare this with that. For destructive interference, the two waves are cancelling each other. For constructive interference, which I'll write over here, constructive interference, this will happen either when the two sources coincide, which is this, or they differ by 1 wavelength or 2 wavelengths or 3 wavelengths. Now let's look at an animation and see just how this works out for sound. Here's an animation that will teach us some sound basics, in particular interference. But before we go to interference, let's hear the single source. So here is the frequency which I'm increasing. I will turn on the speaker. I can change the frequency. And I can decrease the amplitude. Okay, so let's now focus on the following. This is the observer. That observer can be moved further away or closer. Of course, closer you get more intensity. That's because the waves are spreading out. As you can see, these look like circular waves, but they're more like spherical waves because it's in 3 dimensions, and so the intensity is decreasing as the distance from the source is increasing. And probably it is a 1 over r decrease rather than 1 over square root r. But this is not exact because in the real world, the sources don't radiate equally in all directions. All right, now let's go to 2 sources. So here I'm going to turn on the audio. And now you see this observer is located somewhere in between them. Now you see, of course, that the sound that he hears is decreasing in intensity as he moves off. That's perfectly obvious. But what is not so obvious is something else. So let me move him up a little bit. You see, as I move him up a little bit, it gets louder, then it becomes, the sound goes to 0, then it goes up again, and then it comes down again, and up and down and up and down, and you can see that in places the sound is loud, in other places it has almost disappeared. Actually, you can see that from these dark spots and bright spots, or rather dark patches and white patches. The white patches are those of high intensity, and those dark areas are of low intensity. Now this is interference, and sometimes if you're in the right position, then it is constructive interference. If you're in the wrong position, then it's destructive interference and you don't hear anything. Now finally, I'm going to move this observer closer to the speakers, and you'd expect that the intensity would increase. And yes, it does increase. But again, see over here. Here it's high, a little bit down, it's low, and here it has almost totally disappeared. That's because there's destructive interference, and so the waves are cancelling as they reach his ear. Now, of course, because he has 2 ears, that means that the cancellation will not be perfect. The distance between the 2 ears is very important, actually, for telling us where things are located. So when you hear sounds coming from a distant source, you can actually tell how far apart those 2 sources are intuitively. That's because the interference is different in one ear as compared to the other ear, and that gives you a measure of the separation of the sources. Here's an applet that shows how 2 sources can interfere. So this is not sound and this is not in 3D, but this is in 2D. So these are water drops. Let's start by letting drops from one tap fall, and they create these outgoing waves, and these are 2-dimensional waves. Now I'm going to turn on the faucet, the second faucet, and now you can see the interference form. So the dark patches are where there's destructive interference, the light ones are constructive, and there is energy moving out. So it's very similar to what you saw with 2 loudspeakers. There's a very famous experiment in physics that I'll come to next. It's called the double slit experiment, done something like 150 years ago, and it was very important in establishing the wave nature of light. It's also very similar to what you've just seen. That is, waves coming from 2 sources meeting up at one point and either interfering constructively or destructively. However, in this case, it is light which was used. So here's a screen with 2 small holes in them. Let's draw this with a source over here that's putting out waves, in this case light waves, but they could be sound waves. And there's a detector here, so a screen here where the waves reach. Now the waves that reach this slit over here travel from here to some point here. Let's take a definite point on the screen. And so they will travel a certain distance. Let's call that R1. On the other hand, the waves that enter this slit will have to travel a larger distance, and that distance I'm going to call R2. The line that connects the center point over here to this point, I've drawn that as dotted. Let's call this the distance a over 2 and this also a over 2, so that the distance between the slits is equal to a. Okay, so I can also draw a dotted line here, and let's call this the angle theta, which makes this the angle 90 minus theta, and it makes this angle 90 plus theta. Okay, now the point is that the light which travels from here to here has to travel a longer path as compared to the light that started out from here and ended up over here. Let me drop a perpendicular to make things more definite. So this is the extra distance from here to here. Let me call that delta. We need to calculate delta because this is going to tell us the extra distance that the light has to travel. Okay, so look at the first triangle, which is going to be this triangle. And it has, now I'm going to use the cosine formula. So the cosine formula says that the square of this is equal to the square of this plus the square of this minus 2 times the cosine of this angle. So write it down. R1 squared is r squared plus a squared by 4 minus 2 into one side multiplied by the other side times the cosine of the angle between them. And I said this is theta, so this is 90 minus theta. Now cosine of 90 minus theta is the same as sine theta. So this is r squared plus a squared by 4 minus ar sine theta. Let me now do exactly the same thing with the other triangle being this one. So look here. This. The 3 sides are defined here. Okay, now that means r2 squared is r squared plus a squared by 4 minus 2a by 2r. But now the angle is cosine of this. So that's cosine of 90 plus theta. And now you know that cosine of 90 plus theta is minus sine theta. Okay, so this then makes it r squared plus a squared by 4 plus ar sine theta. Now let me take the difference between r2 squared and r1 squared. You know that r2 squared is a little bit bigger than r1 squared, so we're going to do an approximation there. We're going to, well, first of all, write this exactly as r2 minus r1 into r2 plus r1. And as we've just seen over here, the difference between them, so this is the same as this, but this minus that's going to equal to 2ar sine theta. Okay, now r2 minus r1, that's exactly what we want. That's delta. So this is delta. But what about r1 plus r2? Now, if the two slits are close to each other, in other words, if A is small, then r2 is almost the same as r itself. So this is r here, which I should have labeled earlier on, but now it's there. So we have, this is 2r. Okay, so that says that delta into 2r is equal to 2ar sine theta, which means we've established that delta is equal to a times sine theta. Now that's important. It's telling us that this is the extra distance that has to be traveled. As you learned just a little while ago, you're going to have constructive interference. So for constructive interference, we must have k times delta is either 0 or pi or 2 pi. In other words, n pi, where n can be 0, 1, 2, 3, 4, etc. That means that k, now k I'm going to write as 2 pi by lambda times a sine theta. So k into delta must be equal to n pi. And that gives us, if I take lambda to that side, that gives us lambda is equal to 2a sine theta, or rather n lambda is equal to 2a sine theta. And this is a very interesting, very important relationship, because what it's saying is that suppose I look at those places where I have maximum intensity. Well, those will be where sine theta is n lambda over 2a. So at theta equal to 0, I'll have a maximum, then I'll have another maximum, and then another maximum, and in between there will be minima. So there'll be constructive interference here, and here, and here, and here, and in between them there will be destructive interference. So now let's have a look at an animation that will illustrate actually what we have just learned. Okay, so here is a demonstration of the formula that we just derived, which was n lambda is equal to 2a sine theta. Now here that a is called d, so it's n lambda is equal to 2d sine theta. D has been set to 3 millimeters. This is the wavelength of the incoming light or the waves, whatever, 607 nanometers. There's light, there are waves that go through this slit, and they interfere. Here is the screen on which the interference is recorded. So there are constructive patches and there are destructive patches. The dark is the destructive, the light is the constructive. And now we can experiment with this. So suppose I change lambda. Well, that means the distance between the wavefronts becomes less. And so you see the pattern on the screen is also changing. Now the color is changing, of course. With the color, the interference pattern is changing. And now what if I changed D? Well, then the interference conditions become different. So I'm going to take D to be larger, in which case the graph spreads out in this way. Now you might have noticed that the bright patches over here correspond to large intensity of the wave. Remember, the intensity is the amplitude squared. So the amplitude here is also large, which is why the intensity is large. Before leaving the double slit experiment, let me emphasize two things. First, that the source must have the same frequency and polarization in order to interfere. And in the double slit experiment, that's assured by sending in light of just one frequency. And then, of course, it has to be of the same polarization. So you have put it through a polarizer over here. So in the case of transverse waves, you would pick out one direction of polarization only. Therefore, you have these two sources of light, one here and the other here, which are emitting waves coherently. We therefore have the superposition principle applying, and of course the rest you know. You know that in order to get the intensity, you must add the amplitudes and then square. As promised, I'm now going to talk about Huygen's principle. Now, Huygen was a Dutch physicist some 250 years ago or so, I don't exactly remember. But before I come to his principle, let me show you what led him to get to this idea. Okay, so suppose you have, now we just saw this double slit experiment, so you had a wave coming to this slit, another wave coming to this slit, and from this slit over here, out go waves, and from this slit out go waves as well. Now suppose you didn't have 2 slits here, suppose you had 3, and I'm going to draw 3 now. So waves coming here, waves coming here, waves coming here, and then going out like this. Now these are themselves forming a plane wave. Now imagine that this goes and hits another screen which has got more slits in it. And so the idea is, Huygen's idea was that so his principle can be stated as follows, that every point on a wavefront is itself a source of a new wave. That actually sounds very strange, but let me repeat it, and maybe by repeating I'll get some of it across. So here is a plane wave that's moving along, and what Huygens is saying is that if I take this point here, and this point here, and this point here, and this point here, well, each point on the wavefront is the source of circular waves or spherical waves that are going out. So this one was the source of this wavefront. Similarly, this one is the source of this wavefront, and this is the source of this wavefront, and there was maybe another one over here, and that was the source of that wavefront. And so if you look over here, there's another wave that's forming, that's a plane wave. And now this plane wave will itself be the source of another plane wave. So Huygens' principle says that every point on a wavefront is itself a source of a new wave. And you'll ask, where did this come from? Actually, it has a very sound mathematical backing, which we cannot possibly get into because we would need a lot of mathematics for that. But you remember that the little mathematics that we have learned says that if I have anything, let's say sound waves, then d2 epsilon by dx squared minus 1 over c squared d2 by dt squared epsilon, that's equal to 0. So that's the wave equation in 1 dimension. The wave equation in 2 dimensions will have d2 epsilon dx squared plus d2 epsilon dy squared, and so forth. So from the wave equation, it is actually possible to prove this. Prove that every point on a wavefront is itself a source of a new wave. Now, how is this useful in helping us understand anything? Well, actually, it's very useful if you just think about one slit itself. Now, here we had 2 slits. The 2 slits caused waves from here and waves from here to go and interfere on a screen that's somewhere over here. But what if you put a screen on this side? Now there's only one slit. Well, Huygens' principle says that this point and 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 all the points in between these 2 slits are themselves the source of plane waves. So if you take a point over here like this, then the wave from this point will reach here, but the wave from this point, let's say in the middle, will have to travel a slightly longer distance. So there'll be this extra distance, which we had earlier called delta in the case of 2 slits. There'll be a delta over here as well. The point is that every single point in between these two edges is going to be the source of waves, of light waves. And so what you're going to see on the screen is what is called a diffraction pattern. That's what diffraction is. Diffraction is another form of interference. It is interference, in fact. Now, actually, one can do a calculation very similar to the one that we've done, but we don't have time for it. Let me call this here the angle theta. Well, you'll ask, is it with this ray over here or with this? Answer is, doesn't make a difference because these two lines are very close together, and so there's one angle theta. So light from this point or from this point, they travel at approximately the same angle. Now, if you do a calculation, then you get a maximum at either theta equal to 0, so that is to say on this point over here. So all the waves that are coming out from the different points along this slit, they interfere constructively at theta equal to 0, but not just at theta equal to 0, also when d sine theta is equal to n plus a half lambda. Lambda is, of course, the wavelength as before. So this is the condition for a maximum. So when theta takes certain values, well, not only will you get a maximum here, but you'll also get a maximum here and other places. So in effect, what this says is that light, when it comes to a slit, a single slit, it spreads out. It doesn't just go straight, it also bends and goes here and bends and goes here. Let's look at an animation which illustrates this. Here's diffraction of light by a single slit, and Huygen's principle, although we didn't derive that formula, then tells us where the maxima will lie. Of course, there's the maximum here, and this is the first maximum after that. So this is, of course, here, and this is at the same angle here. Now, what if I decrease the wavelength? So lambda gets smaller, and you see that the maxima move in. Now, these are the first maxima. I can keep decreasing lambda, and the angle keeps decreasing. But now, two maxima are shown on each side. Below, you can see the intensity. So at theta, around theta equal to 0, you have this, and then the first maximum to the left is this, second maximum to the left is this. Actually, here there's the option of looking at the intensity in terms of a graph. And so you can see that at theta equal to 0, you have the intensity peaked like this, and then there are subsidiary or secondary maxima as you move out. And you can, of course, see how these change as we change the wavelength. So again, you can see how this is all changing, and it will be very good if you experiment around with this animation yourself.